In this video, we will derive the test statistics used in event studies. In the previous video, which focused on the underlying theory of event studies, we derived equation 7. Thus, under the null hypothesis, abnormal returns follow a normal distribution with mean 0 and variance vi, where I stands for security I. Now it's again important to note that the null hypothesis states that the respective event doesn't have any impact on the share price. Hence, you would expect a return of 0. Now, the variance component was also derived and is shown in equation 8. We will have a more careful discussion before we dive into test statistics. It's for me always important to really understand equations in detail. Sadly, most people just apply equations without understanding where these things are coming from, which I find quite disappointing, to say the least, and also of course it can lead to serious mistakes. So we will try to understand equation 8, and the best way to do this actually is to look at an example. I prepared this example in Excel. The Excel file is also available to download from GitHub. In the description, you'll find a link to the GitHub repository. I will do a separate video where I discuss this Excel model in a lot more detail. So now we just use it and play around a little bit just to get an understanding of how these event studies work. So I took daily data for Tesla and used a constant mean return model to estimate normal return. We covered this in a previous video. I have done a few videos on getting financial data for free using Python or Excel, and then also working on the data in Stata or Python. So check out these videos if you want to automate the download using Python, for instance, or if you want to work more on time series modeling. So when you go to the worksheet event study, this worksheet conducts an event study analysis, starting with the estimation window to establish the normal return. Certain inputs can be modified, so these are parameters and you can modify them. And in particular, we can pick a start date for the estimation window and the length of the estimation window. In this worksheet, the upper bound is 1000. Well, it would be quite unusual to have a very long estimation window. So in most applications, it's usually around 60, 90, 120 or 180 days. The start date is a date format, so it follows the usual formatting, so days, months, and years. So in this particular case, I refer to the 14th of January in 2022. And then I have an event date. Now, event dates can be, of course, adjusted as you like. Now, in our case, we might focus on a particular event that might be relevant in the context of the Tesla share price. So one interesting event is the announcement that Elon Musk takes over Twitter, nowadays X, on the 14th of April 2022. Of course, it took quite a long time to implement this announcement, but usually when it comes to M&A, so mergers and acquisition announcements, we focus on the first announcement of a transaction to assess the market response. So here the idea is that the market looks at this event and tries to understand what are the implications for Tesla. Of course, Tesla is not, in this case, the acquirer. However, the CEO is maybe a little bit too busy to take care of Tesla after trying to take over Twitter. So what we specify in this case is our event date. So that's the date of the announcement. And then we have an event window. I use by default symmetric windows, and the maximum number of days would be 30 days plus minus around the event date. So in the event window, you see I start 31 days before because I always lose one observation due to return calculations from share price. So in this particular worksheet, modifying these parameters, of course, will adjust the whole calculation. To derive the normal return, I use the constant mean return model. It's very simple, but actually quite acceptable in most circumstances. And then I just follow the discussion we had in the previous sessions. So here, for instance, that's the expected return, which is just derived from our return during the estimation window. I can then obtain a sample variance. Again, this is just using standard Excel formulas. And as I mentioned before, I will do another video where I explore the Excel file in a bit more detail. So I select as event date the announcement of the takeover. And on the abnormal return side, we obtain the abnormal returns from our observed return minus the expected return, which is just the constant mean return. And of course, we can modify the length of this window and it would adjust accordingly. I will talk about the other columns in a minute. In this particular case, I use log returns, which I discussed in another video if you want to explore this a bit further. Now it's important to recall that for equation 8, we work with a data matrix. So there are two different types here. There is xi, which is happening during the estimation window, and x star I, which focuses on the event window. The data matrix refers to the all-one vector. Now this is true for the event and also the estimation window. The estimation window has length L1, hence the data matrix X has dimension L1 times 1, which means it is a column vector. In a similar way, during the event period, the data matrix X star has dimension L2-1, again another column vector, where L2 is the length of the event window. So here we are, I just wrote down our equation, and I want to take the second part term by term. So let me first focus on this inner bit here, which refers to the data matrix in the estimation window. So I will just write it down first, and we do it step by step, just nice and slow. I can now drop the I because I just focus on one security, so we have x prime x. And in our case, because we focus on a constant mean return model, as discussed, the x, the data matrix, would be a column vector. So x prime would be a row vector because that's the transpose. Again, I did videos on the transpose if you're interested. So in this particular case, we get the row vector of all ones, so it's just ones, times a column vector of all ones. Yeah, and we know the dimensions as well. So the row vector would have one row and L1 columns, the column vector L1 rows and one columns, one column, singular. yeah, mathematics is more important than English, of course. So columns is fine. Good. Of course, that's matching, so we can multiply this out. And if you multiply this out, and we have done this in other videos, we just take here the first element, multiply this one, and then we add the next one. So you add up all these ones, and you do this basically L1 times. So that's what you do, and you end up by construction with a 1-1 matrix, which is a scalar. So here you end up with L1, which is simply the length of your estimation window. And when you look at the equation up here, it then asks for the inverse. Well, it's a scalar, so it's a number. The inverse of a number is simply 1 divided by L1. So that's easy enough. Now, if we look now at this term again, we can simplify this a little bit. And so we can write the following. So I'm just now moving to the next term here. So it's x star. Again, I ignore the I because we just look at one security. And then we have here x star prime. And this term in the middle is simply 1 divided by L1. That's a scalar, so I can pull this front. Yeah, so that will be perfectly fine. So I have 1 divided by L1. And here we have now a column vector of all ones. Now this is during our event window, so we know dimension is we have L2 times 1, and then we have the transpose, which is a row vector, so it's 1 times L2, so we have the all-1 row vector. So if you multiply this out, you end up with an L2 times L2 matrix of all ones. Yeah, so it's always 1 multiplied by 1 and so on and so on. So you end up with 1 divided by L1 times an all 1, just use that as notation, matrix that has dimension L2 times L2. Now we know from our discussion previously that this here is an identity matrix and it has dimension L2 times L2, so it will just match absolutely perfectly. So in terms of components of our variance term, the second term we just discussed is the sampling error. Now this sampling error, of course, will depend on our estimation period. To be precise, will depend on the length of the estimation period. Thus, for a sufficiently large estimation period, the second term will vanish. Now this makes perfect sense, as the second term is the sampling error term, so a larger sample means the sampling error should get smaller. Now let's move back into our Excel file and try to assess the impact of the announcement taking over Twitter or X on the Tesla share price. Now, to assess the impact of any event, it is common to cumulate the effect over time, starting a few days prior to the event. Now, in this particular setup, I use a symmetric event window, so I have the same days before and after the event, which is a common way of determining an event window. This cumulation of abnormal returns is called the cumulated abnormal return, or CAR in short, and you see this in this column here. It's just adding up our abnormal returns over time. We assume that under the null hypothesis, each abnormal return is drawn from a normal distribution. Hence, adding these abnormal returns over time results in a CAR, which is also normally distributed. Yeah, so the sum of normally distributed variables that are all independent, again, is normally distributed. The variance increases over time, assuming that abnormal returns are IID distributed. Now this is, of course, plausible under the null hypothesis. Now IID means identically independently distributed. Because under the null the event doesn't have any impact, we would not assume that an abnormal return today affects anything in future. There should not be any relationship. So an IID assumption is perfectly plausible. Now, of course, if you add up these normally distributed error terms over time, you end up with a random walk. So under the null hypothesis, the car is actually a random walk. Now, you can derive upper and lower bounds of random walks quite easily, and you can then use these basically confidence intervals for hypothesis testing. So it's a different way to look at test statistics and hypothesis testing. Let's have a look at the whiteboard and just play around a little bit more. So when we look at our car, what we do is we sum over time our abnormal returns, which are defined in our event window. Now in our case, time might start at maybe -8 and it might go up to +8, or we might modify this further. But end of the day, what we have is we have abnormal returns being added up over time. Yeah, and so on and so on. And as long as these abnormal returns are IID distributed, we can say something about the distribution of our car. So we end up with car being normally distributed with an expected value of 0, because expected values are all linear operators. So the expectation operator is linear. So if we just add up all these terms, take expected values, we just have, of course, 0, because all the individual ones are equal to 0. And we end up with, in this particular case, now depending on how many terms we have then the length of our window, which we call L2 for the event window, times our individual variance. Now our individual variance, we just used V for that, or VI. We only have one security, so we can just leave it there. Now this is of course true if it's IID distributed, and of course if we want to get a standard error from this, we have to take a square root. So we end up with something that looks like the square root of time, basically, and here the square root of my variance. Yeah, so that's basically the one we would be interested in. If we talk about confidence intervals, and it's approximately normally distributed here to be precise, we basically take plus minus 1.96 times the standard deviation for the upper and lower bound, and this gives me a confidence interval for 95% of confidence. Yeah, so this would be a very plausible one also for hypothesis testing. So hence we can derive these confidence intervals in a straightforward manner. These bounds can be then used for hypothesis testing. So this is based on what you call the duality principle of hypothesis testing. So you can do hypothesis testing using a test statistic or using confidence intervals. It works both ways. So if a car is above or below these bounds, this car would be then significantly different from 0 based on a certain level of confidence. Let's jump back into our Excel model and play around a little bit. So let me just modify this here and go up to 30. So that's a wider window for my event, and I can just now visualize it. So I just take here my abnormal return over time. So that's the car. I have the lower and the upper bound. and I can all throw this together into a little chart. And the interesting thing is that in this case you see that the car is overshooting initially and then it goes back down. So put differently, now our event in this particular case, we can just change, of course, our dates and refer here to our event window to make it a little bit easier. So you see that actually at 0, so this is when it was announced, it's dipping. Yeah, so you have something slightly positive prior to the announcement and then followed by a negative response, but no longer significant. So you have what is sometimes called a run-up. Yes, you have positive, significant abnormal returns prior to the announcement. So this is quite common for anticipation of events, not uncommon in the context of merger announcements in general. But again, of course, this is a very particular setting because we don't look here at the bidder. We only consider that the CEO might get distracted, which might be the case when you take over another company. But based on our evidence, we can conclude there is no significant impact of this announcement on Tesla's share price. Now, this, of course, was written very differently in the media, obviously, but Tesla tends to also have quite a high degree of daily fluctuations. So looking at this from the perspective of an event study, it is not convincing to argue that the announcement had any negative impact. In contrast, we can argue there was a positive anticipation, which is interesting. So let me know your thoughts in the comments. If you have any questions, if you want to see something else, if you want to shape the content of this channel, consider becoming a member, join the herd of data nerds and decide about the future direction of our lovely project. If you're looking for complete and affordable courses focused on data analysis, please check out my Udemy courses. Links are in the description and on my channel pages. End of the day, as you can see, never trust media reports. In our case, we showed that there was no significant impact on Tesla's share price, triggered by the announcement of taking over Twitter. So never trust, always verify using your own data analysis. This is the way.